For this lesson, we're going to talk about confidence intervals for the difference between two means. And this lesson is going to focus on independent samples. But before I start, I want to tell you about the two different things that we'll do in this chapter. A drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drug. Here's one way in which the study can be designed. 2 samples of individuals are chosen. One sample is given the old drug and the other sample is given the new drug. After several months, blood pressures of the members of both samples are measured. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, the samples are independent. This means that the observations in one sample do not influence the observations in the other. Here's another way in which the study can be designed. A single group of individuals is chosen. They're given the old drug for a month, then their blood pressures are measured. Then they switch to the new drug for a month, after which their blood pressures are measured again. This produces 2 samples of measurements, the first one from the old drug and the second one from the new drug. We compare the blood pressures in the first sample to the blood pressures in the second to determine which drug is more effective. In this design, the samples are paired. Each observation in one sample can be paired with an observation in the second. And if they're paired, they are not independent. Like in this one, you can see that people were paired to themselves. A lot of times in a paired design, it is the same person. They go through each treatment separately, like in this problem, or sometimes they'll compare people who are similar. They'll compare similar people in a cancer treatment or something like that, but the problem clearly matches people together. Now, I want you all to pause the video and try questions A and B. Once you're ready, turn them back on and I'll talk about them. For A, it says a sample of students is enrolled in a speed reading class. Each takes a reading test before and again after the class. The 2 samples of scores are compared to determine how large an improvement in reading speed occurred. Are these samples independent or paired? And clearly from that, you can tell that they're paired because they're comparing a person to themselves before and after the class. The second one says a sample of students is enrolled in an online stats class and another sample is enrolled in a traditional stats class. At the end of the semester, the students are given a test. The scores from each sample are compared to determine which class is more effective. Are these samples independent or paired? These would be 2 independent samples. And again, you can tell from the context of the question which it is, and that's going to be important in which test we do. Now, what I want to do first for this lesson is we're going to construct confidence intervals for the difference between the 2 population means. And like I said at the beginning, we're going to focus on the independent samples. Now, it says, imagine that we will compare a new blood pressure drug to a standard drug. We will draw 2 independent samples. The first will get the new drug and the second will get the standard. We can imagine these samples as coming from 2 populations, a population of patients who take the new drug and a population of patients who take the standard drug. For each population, there's a mean reduction in blood pressure. We are interested in estimating the difference between the population means. Let mu1 be the population mean reduction for the new drug and mu2 be the population mean reduction for the standard drug. We want to construct a confidence interval for the difference. And remember, the confidence intervals are always about mu, never about x bar. We use x bar to make a prediction for mu, make that confidence interval. The point estimate for the difference, mu1 minus mu2, is the difference between the sample means. In other words, the point estimate for mu1 minus mu2 is x bar 1 minus x bar 2. And the confidence interval, just like before, is that statistic. This time our statistic is x bar 1 minus x bar 2, plus or minus the margin of error. This method is often referred to as Welch's method, and Welch's method requires the following assumptions. And they're basically the same, except I've got one additional assumption, and a little change on the two that we're familiar with. And here's the first one. The first one, you have to have random samples. And you can say SRS like we always do, but you need to say random samples from both populations. And the second one, this is a new one, the two samples have to be independent. That means what happens in one has no impact on the other. And the third one is our normal condition. And we would want each sample to be large. Greater than 30 for CLT, same as before. Or the populations are approximately normal, just like before. Or you examine the data and use your best judgment and make a graph from both populations. What we're going to do with this problem, we're going to go back to our the drug problem for the high blood pressure, and same problem. It says to test this drug, a sample of 15 patients is recruited to take the drug. Their systolic blood pressures are reduced by an average of 28.3 mmHgs with a standard deviation of 12. In addition, another sample of 20 patients takes the standard drug. The blood pressures in this group are reduced by an average of 17.1 mmHgs with a standard deviation of 9. Assume that blood pressure reductions are approximately normally distributed. And I want a 95% confidence interval for the difference between the population mean reduction for the new drug and the standard drug. And this is two independent samples, right? I've got two totally separate groups. This is a 2-sample t-interval. And it's t because they're giving you the standard deviation, and it's that standard deviation is coming from the sample because it doesn't say sigma, it doesn't say population. So here's what I'm going to do. I'm going to start with checking my conditions or assumptions. And it doesn't specifically say that they did random samples in this. Probably they did random assignment, the groups, because it's an experiment. But you can assume that. So I'm going to say 2 random samples. I think that they're both independent. And here's what I mean by that. I think what happens in one sample is not going to have any impact on the other. The normal condition, you need to check for both groups. And notice that it says that the populations are normal, or approximately normal. So I'm going to say both populations are approximately normal. So we're good to go. Now, what I'm going to show you next, there's 2 ways to do this. Here's what I like to do. First of all, we're going to figure out how to subtract it. And it doesn't matter how you subtracted it. You could end up with a confidence interval that was negative or positive, and you'd be right. You know, Alex is going to be a little picky. So here's what it says. I want the mean reduction for the new drug and the standard. So I'm going to do new drug minus the standard drug. And here's what I like to write out. Some people like to write this at the end. I like to write it here because it helps me on the calculator. So here's what I know for the new drug. I want their sample mean. I want their sample standard deviation, X bar 1, S of 1, at the sample size. And ultimately, I want to know mu. All right, and I get, from the problem, I get 28.3, 12, and 15. And I'm going to do the same thing with the standard. X bar 2 is 17.1. S of 2 is 9. N of 2 is 20. And ultimately, I want mu of 2. Now, before we start, take your calculator, and I want you to do 28.3 minus 17.1. Okay, now here's what I know. I know that with this experiment, the new drug was better, okay? It reduced the blood pressure 11.2 mmHgs more than the standard drug. How do I know that? I subtracted it. I got a positive number. Okay, so I know that the new drug did better. But what I want to know is what happens if I do this with the entire population, what's going to happen. And we're going to do a confidence intervals. Here's what we're going to do. I want you to go to stat and tests. And I want you to go down to the intervals. We've done a Z interval when we know sigma, a T interval when we don't. We called it 1 sample Z, 1 sample T. This is a 2 sample T. Okay, so I want a 2 sample T interval right there. And I'm going to input my stats. My X bar 1 is 28.3. My S1 is 12. N1 is 15. X bar 2, 17.1. S of 2 is 9. N of 2 is 20. And I want 95% confidence. And anytime if you need to, just pause the video if I'm entering something too fast. You're not going to pull this. Leave it at default no. And then I'm going to calculate. Some people don't like to write what I wrote in red. They like to give me a whole screenshot. If you guys look at what's on the screen, that would be perfectly fine. I like to write what I wrote in red, and then here is my screenshot. I'm going to just write the addition that we have here. Okay, so I did a 2 sample T. You always want to say what you did. Okay, so if you do that screenshot, it tells you 2 sample T. My interval is 3.5912 to 18.809. And the only thing I'm going to add is that DF. And notice that the DF is a little bit different than what we did before. It's different if you do, the calculator has a complicated way of doing the degrees of freedom. So that's the difference in that. But here's what I'm going to say for my conclusion. I'm going to say, and it's been a minute since we've done confidence intervals, but I'm going to say we are 95% confident that the true mean difference, or the population, the true mean difference for the new drug and the standard drug is between 3.59. I'm put those units on there. mmHgs and 18.81 mmHgs. All right, now what does this mean? Okay, so here's what this means. It means that the new drug is better. All right, how do I know? The confidence interval is positive. When I subtracted it, made the confidence interval, the whole thing's positive. How much better is the new drug? It reduces blood pressure by between 3.59 and 18.81 mmHgs more than the old drug. Okay, so the new drug is good. For this question, we've got a sample of 87 one-year-old spotted flounder, and it gives you the mean length and the sample standard deviation. A sample of 132 two-year-old spotted flounders gives you the same data. Notice it says sample standard deviation. Even if it didn't say the word sample, you assume that it's from the sample unless it specifically tells you population or sigma. Okay, but this is samples. This is T. I want a 95% confidence interval for the mean length difference between 2-year-old flounder and 1-year-old flounder. So this is a 2 sample T. And here are my conditions. First one, I'm going to assume 2 random samples. Okay, so 2 random samples. The second one, both of them are independent. They didn't say they tagged the flounder when it was a year old and then let it grow and measured it again at 2. They didn't pair these. They didn't pair them. They're 2 independent samples. In both samples, the sizes are large. N's greater than 30. So CLT tells us that the normal condition is met. Now, again, watch how you're going to subtract it. I'm going to do 2-year-old minus 1. Now, keep in mind what this is telling you. Like, say that I did my age short minus Gina. I'm going to get a positive number because I'm older. If I did Gina minus short, I'm going to get a negative answer. I'm still older. If I did Gina minus someone her age, I'm going to get a difference of 0 because they're the same age. So keep in mind what it means. Now, be careful with this 2-year first because I'm going to call this X bar 1, S of 1, N of 1, and ultimately I want mu of 1. And the same thing here. X bar 2, S of 2. Just be careful with those 2's. N of 2 and mu of 2. And now notice up here, it gives us the 87 1-year-olds first. I'm going to start with this. So I've got 87 1-year-old had a mean length of 126.31 and the standard deviation of 18.10. The 2-year-olds, I had 132, mean length of 162.41, and a sample standard deviation of 28.49. And we're going to use our calculator, and I'm going to go to stat tests, and again, this is a 2-sample T. I'm going to input my stats. X bar 1 is 162.41. S of 1 is 28.49. N of 1 is 132. X bar 2 is 126.31. S of 2 is 18.10. N is 87. We're not going to pull. I want 95% confidence. And I'm going to calculate it. And here's what I'm going to get. And I told you on the last one what to do about your screenshot. Some people want to do the whole screenshot and not write what I wrote in blue. If you do that, just write everything. This is a 2-sample T interval. You always want to say what you did. There, I've said it. 29.894 to 42.306. And my DF is 216.753. So here's my conclusion. We are 95% confident that the population mean difference between 2-year-old and 1-year-old flounder is between 29.9 and 42.3 millimeters. And here's what that means, okay? This means that because it's a positive interval, right? Both terms are positives. The 2-year-olds are longer. How much longer? Well, between 29.9 and 42.3 millimeters. The last thing, I'm going to show you something on this last page that will help you for your interpretation. I want you to pretend that I did something with heights, okay? And I wanted to find the true mean difference between heights of SU males and UMES males. And I wanted to make a 95% confidence interval. So here's what I wanted. I wanted SU minus UMES. I want heights. And I want a 95% confidence interval. All right, and I'm going to make up some. Okay, so say that I got this as my answer. I checked all my conditions. I did my confidence interval, and I got this. Okay, I get a positive confidence interval. This means that, and I would give a good conclusion. Okay, I don't want you to conclude it. I just want you to tell me what it means. This means that males at SU are taller. Okay, how do I know? Because it's positive. How much taller? Between 2.5, and 3.7 inches. Okay, so that's what I know. Now, say that I got this. Say that I got negative 4.8 to negative 2.6. Okay, now look how I subtracted. I did SU minus UMES. To get this negative confidence interval, UMES has to be bigger, right? So here's what this means. UMES is taller. Okay, how much taller? Between 2.6 and 4.8 inches. Now I'm going to tell you, both of those I made up, and they're both probably unrealistic because I think the heights would be the same. I think the heights would be something like this. Okay, so look at this confidence interval. Okay, now what does this say? Well, negative tells me UMES might be taller. Positive tells me SU might be taller. More importantly than that, I have a 0 in this confidence interval. 0 tells me there's no difference. Okay, so here's what this is. This tells me no difference because the easiest way to explain it is because 0 is an interval. And some people get confused. Like, say that the confidence interval was like this. Say it was like negative 1/10. Then it went up to 14 inches, okay? Again, not realistic, but just say it went like that. Some people would say, I think it's more likely that SU's taller because it's a lot, the interval goes higher in the positive numbers. No. All you want to say is there's no difference because 0 is in the interval.